Okay, guys, if there's anything that I want you to leave this class with, I mean, I want you to leave this class with a lot of things, but I really want you to leave this class with an understanding. Yep, got that. Thanks, Sean. With an understanding of models and like an appreciation that we use different models to explain different things. Okay, so we use Lewis structures because those are really good models for helping us imagine how many bonds a molecule has, how many electron domains it has around the central atom, whether those are going to be single bonds or double bonds or triple bonds, whether or not we're going to have resonance. It tells us the shape of the molecule. The shape is going to contribute to the polarity of the molecule. Like, it tells us a lot of stuff. Like, Lewis structures and molecular geometries are super useful, but they don't tell us everything. Like, there are a couple of things, like whether or not that substance is magnetic, how that substance can emit light by electrons moving up in energy levels and down in energy levels, just like atoms of an element can. Molecules can do that as well. We need a different model to explain those properties. And this model is called molecular orbital theory. And all it's saying is we take those areas of mathematical probability where the electrons exist in an atom, right? So imagine I have like a hydrogen atom over here. That's a 1s orbital, an atomic orbital. And I have a hydrogen atomic 1s orbital over here. When those atomic orbitals overlap, we're getting like a combination of mathematical probabilities. We're getting a new area around the nuclei, hopefully between the nuclei, where those electrons can exist. And if the electrons exist there in this new area of probability, then we have a bond. If they don't exist there, if it's more likely that the electrons are outside of the nuclei and not between them, if the probability is such that they are not between the atoms, then you don't have a bond. Okay, so we're going to take atomic orbitals and we're going to mathematically blend them together into what we call molecular orbitals. So you need to know a little bit of math around that in order to understand what's going on. Okay, so here's the math. Go ahead and draw these two waves. You guys need to recall that, like, the reason we had an s orbital in the first place, like these orbitals that we got, you know, the s being a sphere and p's being dumbbells, right? And we remember we got three different ones, px's, py's, and pz's. All of these different orbitals, and the d's and the f's, all of these different orbitals became what they were, or these shapes emerged through the graphing of the electron's wave function squared. Okay, so that's where these things came from. Like, we graph the wave function, we find all the areas of probability around the nucleus where the electron can be. And we're like, oh, they could be in this spherical shape, or oh, the electron could be here in this dumbbell lying along the x-axis, and so on and so forth. But those are graphs of what we call wave functions. So here we have two waves, right? So imagine that we are combining the wave function of one hydrogen 1s with the wave function of another hydrogen's 1s orbital. When you have two waves where the peak and the peak are in the same place, and the trough of the other wave are in the same place, when we add these two waves together, these waves are called in phase. These waves are in phase with each other. The math behind this, and you guys will learn this when you take all sorts of crazy calculus in college. When you do the math to combine these two waves, you end up with one bigger wave. This is what we call constructive combination. And again, don't get too theoretical, bring it back to what we know. This is representing the wave function of one hydrogen 1s, and this is the wave function of another hydrogen 1s. When we combine those waves, we get one bigger wave. However, there is also a chance that these waves are out of phase. Essentially, where you have a peak in one wave, you have a trough in the other. That's going to cancel these two things out. These two areas of probability, they're going to cancel. The trough in this wave is where the peak in this wave is. When we mathematically add these two waves together, we get nada. We get nothing. This is what we call destructive combination. Okay, so that's just a fact about combining waves. What does that mean for us when we're thinking about these atoms, right? Like when the 1s orbital overlaps with the 1s orbital, the fact that that can happen constructively and destructively, like what does that mean? If I'm going too fast, let me know. Okay, here's what it means. Let's say we have a hydrogen 1s orbital. And we combine that with another hydrogen 1s orbital. Mathematically, I have two probabilities. I have two things that could happen. When these two wave functions combine, they could do so constructively. In other words, they could combine such that the area of probability where the electrons are likely to be is between the nuclei. Right? Like we get this overlap and we get this symmetrical electron density around both of the nuclei and between the nuclei. So like here between the nuclei, that would be what we call a sigma bond. So there's a chance that we get a sigma bond. But there's also a chance that that wave function combines destructively. In other words, there's a chance that the probability densities are actually out here on the opposite sides of the nuclei. It's like kind of looks like a monster. Do you guys see it? Like the eyeballs in the mouth. Oh, that was funny to me. I've clearly been lecturing too much this week. I'm getting ridiculous. Okay, so here where you have no probability density between the nuclei, we're not going to have a bond. We call this a sigma, and we put a star next to it, meaning an anti-bonding orbital. Okay, so when these 1s's overlap, there's a chance that you get a sigma bond, and there's also a chance that your electron probability density areas are out here, as opposed to here, and you don't get a bond. Okay. Now, the reason why I drew this one down here and these two up here is because the bond is favorable. And so this is lower energy, like this is like an energy diagram going from low energy, up to higher energy. Okay. Now, we don't have to draw all of these goofy shapes. You know, just like when we were doing electron configurations, I didn't make you guys draw the 1s and draw the 2p's. Like I didn't make you draw the spheres and the dumbbells and the butterflies. We don't have to draw all of the shapes of these orbitals. Instead of drawing all of these crazy shapes, we can just do lines with electrons in them, right? Like we can just do this. You know how we do atomic electron orbital diagrams? We can do the same thing for these molecules. So like this right here is representing the same thing as this right here, okay? And so the way that we draw that is with either lines or boxes. So I'm gonna kind of slide to the left a little bit. Here we go. So going from low to high energy. So like, let's say I have a hydrogen. This is going to represent my hydrogen, and this is my 1s orbital for my hydrogen. It's got 1 electron in it. Oh my God, my kids are running around. Other side of my diagram is my other hydrogen 1s, 1. When these two things overlap and combine, we can get this bonding orbital. I guess I should have said sigma bonding, okay? So that's lower in energy. Ugh, that should be in the middle. Sorry, that looks gross. There we go. Looks a little bit better. Okay, here is my sigma 1s bonding orbital. Higher in energy, less favorable, is my sigma anti-bonding 1s orbital. So what I'm drawing you guys is on the sides are my atomic orbitals. This is an atomic orbital, and this is an atomic orbital. When these two things overlap, what you get is a set of new areas of probability where the electrons can exist in the molecule. So we're going to call this a molecular orbital diagram. So here's what we do. We're going to fill up this molecular orbital diagram with all of the electrons from the atoms that are coming together to form the molecule. It's not very many electrons in this case, it's 2 electrons. And you're going to follow your normal fill sequence, which is you fill low energy to high energy. You do up spin electrons first, and you spread them out within an energy level before moving up an energy level, or before pairing them up, I'm sorry. So here we go, we have 2 electrons, so we're gonna go 1, 2, and that's it. In the case of the H2 molecule, there are no electrons in the antibonding orbital. But I want you guys to recognize, I am not showing you anything new. Like this is just a different way to represent this. Hydrogen with 1 electron, hydrogen with 1 electron, sharing those 2 electrons. Like we are representing this, the H2 molecule. You could also draw it like a ball and stick linear model. This is another way of representing this, all of this. Now, just by looking at it, like just by looking at these other models that we're more familiar with, I look at that and I see a single bond. You guys now know, right, that single bonds are sigma bonds. Sigma bond, I only have one of them. That's a sigma bond. I also know that this has a bond order equal to 1 because it's a single bond. But we can actually calculate this bond order Like these actually come from these bond orders that I told you guys. I said, hey, just take my word for it. A single bond is a bond order of 1 and a double bond is a bond order of 2. It actually, this bond order thing actually comes from here. Here's the real calculation for bond order, you guys. For bond order, you take the number of bonding electrons, so electrons that are in bonding orbitals, minus the number of anti-bonding electrons, divided by 2. Okay, so bonding electrons minus anti-bonding electrons divided by 2. So that's your equation. So let's calculate the bond order here for the H2 molecule. I know it's 1, but like, let's prove it. How many bonding electrons are there? Well, look in the bonding orbital, there's 2. Subtract from that the number of electrons in your anti-bonding orbital, there are none, and divide by 2. Voila, a bond order of 1. Okay. So you might say to me, like, why do we need to do all of this mess if like we can just get the same information from here? Well, to be honest, we don't use this model a whole heck of a lot, all right? But what it does allow you to do is it allows you to see that there are actually higher energy orbitals available for electrons to move up into. Like if we were to take this molecule and excite it, like when I took that hydrogen gas and I put it in the gas discharge tube and I ran the electricity through it, you saw light. That wasn't individual atoms of hydrogen. Those were H2 molecules that were emitting light. So really, it was, this diagram would have been more appropriate. Of course, we didn't know about it yet. Would have been more appropriate for explaining how is this hydrogen molecule producing light? The electrons are moving up in energy levels and moving back down. It wasn't individual hydrogen atomic orbitals. It was actually these molecular orbitals, because in that gas discharge tube was H2, not individual atoms of hydrogen. Here's the other thing. It also tells us about magnetism, okay? Do you guys see how, let's pick a different color, okay? These 2 electrons here are both, they're in a pair, like there's no unpaired electrons in this structure. When all of the electrons in the structure are paired, we say, when they're all paired, we say that this substance is diamagnetic. Di meaning 2, right? So there's 2 electrons in a pair, okay? So when all electrons in the orbital diagram are paired, the substance will be repelled by a magnetic field. And if you're wondering, like, why do I care if it's attracted to a magnetic field or repelled by a magnetic field? It's a property of the substance. We actually use it a lot. They'll take diamagnetic, or the opposite called paramagnetic, which we'll talk about in a minute. They'll take these substances and they will attach them to biomarkers. And then that biomarker you can inject into a sample of any sort of bodily fluid, you know, blood, spit, whatever. And then you can take that sample and expose it to a magnet. And whether that substance attracts to that magnetic field or not tells you whether or not that substance is actually in the blood, right? So you would take a diamagnetic substance, attach it to a biomarker for a particular toxin or a particular virus. And if that virus or that toxin is in that sample, when you bring a magnet up to that sample and it attracts or it repels, you'll know whether or not that thing was present. So it's used a lot as a very cheap and efficient diagnostic tool. So anyway, yeah, it's worth knowing is my point. Okay. Opposite of diamagnetic, and of course we haven't looked at a paramagnetic example yet, but that's the opposite, okay? The opposite of diamagnetic is paramagnetic. And that's when you have some unpaired electrons. When any electrons in the orbital diagram are unpaired. And instead of being repelled by a magnetic field, the substance will be attracted to a magnetic field. And what's also kind of interesting about this, you guys, is the more unpaired electrons you have, the more attracted the substance is to the magnet. So it's like an extensive property. Like if you've got more and more unpaired electrons, the more magnetic that substance is. Okay. So let's look at another molecule. All right, we're gonna do this again, but instead of for H2, let's look at a molecular orbital diagram for He2, like a helium molecule. And you're like, helium molecule? Yeah, hopefully you're skeptical, right? Because we know that a helium molecule is not going to form. But this theory can sort of prove to us why, all right? So let's draw our little diagram again. Let's draw my helium. Here's my 1s atomic orbital for helium. It's got 1, 2 electrons in it. And here's my 1s for my other helium, 2 electrons in it. If we combine a 1s with a 1s, we can get the constructive combination. Oh, I keep drawing that off kilter, whatever. Sigma 1s. We can also get the destructive combination. Sigma antibonding 1s. So now we've got 4 electrons to fill up our diagram with. 1, 2, 3, 4. You're like, all right, well, so what? Well, let's calculate bond order. Like, let's show why this molecule does not form. Number of bonding electrons down here, 2. Minus the number of antibonding electrons, 2. Divided by 2. 0. This molecule does not form. You get a bond order of 0, there's no probability of those electrons being in bonding orbitals. Does not exist. I'm going to pause recording for a second and check in on you guys. All right, here we go. So we were just working, you guys, with things in the first period. And in the first period, we only have a combination or an overlapping of a 1s with a 1s. Well, what happens when we're in the second period and we have a 2s and a 2s? I mean, that's obviously going to do the same thing. Like when the 2s's overlap, they're going to create the same sort of arrangement or molecular orbitals that the 1s does. In fact, let's just go ahead and start doing it. Let's look at second period molecular orbitals and beyond. Okay, so let's look at, for example, let's do O2. I'm not even going to worry about the 1s for oxygen because we only bond with valence electrons, right? So I'm going to actually start down here. I'm going to start low energy first. So my 2s for oxygen is lower energy. So here's one oxygen. Here's my atomic orbital for my other oxygen. We're going to get this overlap that gives us the sigma, but we're going to call it a 2s bonding orbital. And we're going to get the overlap that gives us the anti-bonding 2s orbital. But now, higher energy than the 2s is the 2p, right? Oxygen has a 2p as well. So here are my oxygen 2p atomic orbitals. So we do actually kind of have to think about what's going to happen here in terms of like what's it going to create for a molecular orbital diagram. I want you guys to remember that p's, remember p orbitals are these dumbbell things, right? That lie along different axes. Okay, so like here is this is like a px, but there's also a py. And there's also lying, coming in and out of the paper, a pz. If the px orbital for one oxygen overlaps with a px orbital for another oxygen, so like here, this is the other oxygen's px. Do you guys see how this orbital overlap is happening between the nuclei? Remember how we call those sigma bonds? But if we had a py overlapping with another py, you see how that overlap is going to happen above and below my internuclear axis? Remember we talked about this yesterday with hybridization? That would create a pi bond. And if the pz's overlapped with each other, that would also be either in front of and in back of the internuclear axis, right? Here are my nuclei. This would create another pi bond. Okay, so when these p's overlap, right? This being one oxygen's px, the other oxygen's, this would be like the px, the py, the pz for one oxygen. This would be the px, the py, the pz for another oxygen. When these guys overlap, you get one sigma bond and two pi bonds. So let's draw those. So like here's my sigma 2p. I get a sigma and I get 2 pi 2p orbitals. But wherever you get bonding orbitals, you also get anti-bonding orbitals. So next in terms of energy are your pi 2p anti-bonding orbitals. And then your highest energy orbital is the sigma 2p anti-bonding orbital. And don't sort of lose track with all of this. Don't lose track of what we're really looking at, right? All we're looking at is this is one oxygen's atomic orbital diagrams. These are where the atoms are, where the electrons are in the atom. Same thing over here. This is going to be my atomic orbital diagram for my other oxygen. When they combine, they create areas of probability between the nuclei where the electrons can exist, which would be bonding orbitals. And they also create the possibility that the electrons are not between the nuclei, antibonding orbitals. And we call this thing, this big thing in the middle, a molecular orbital diagram. So let's fill this thing out with electrons. So oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Same thing over here. 1, 2, 3, 4, 5, 6. So I have 12 total electrons to put into my molecular orbital diagram. Just follow your rules in order. Low to high energy first. So 1, 2, 3, 4, 5, 6, 7, 8. You guys see how I spread them out within an energy level before pairing them up? 9, 10. Spread them out. 11, 12. Okay, so of equal energy, because remember, this is an energy diagram going from low to high energy. These are of equal energy. Spread them out within that energy level before pairing them up. Okay, so we just learned a couple of things. We learned about its magnetism. We can also calculate bond order. Let's calculate bond order first. So we count up all of the electrons that are in bonding orbitals. 1, 2 here, 3, 4, 5, 6, 7, 8. Count up your electrons that are in antibonding orbitals. 1, 2, 3, 4. Divide by 2. So look, we have a bond order of 2, which we already knew. I get it, we already knew it because we know that a double bond has a bond order of 2. But look, it's important to see that our different models complement one another. Okay, like this model doesn't tell me anything about like the linear geometry here, but it does confirm my double bond order. Here's the other thing it tells us. Because of these unpaired electrons here, I know that this molecule is paramagnetic. It's going to be attracted to a magnetic field. Now, all of the examples that we looked at today were called homonuclear molecules. Like it was an oxygen to an oxygen, a hydrogen to a hydrogen, a helium to a helium. But you can do heteronuclear molecules as well. You could do a nitrogen to an oxygen. You can look at these molecular orbital diagrams for really complicated molecules. We're not going to do that. In fact, that's all I'm going to do. And I'm going to stop recording and take whatever questions you guys have.